Hey guys, this is Don Crowley. I'm going to run you through my final project for CSC 578. All right, the first thing I'm going to do is show you my final model with the best performance. This model had three layers. I used first layer was a 250 node LSTM layer. Second one was a 250 node GRU layer. The third was a 250 node GRU layer, and then the final one was just a one node dense layer. Um, so I didn't do anything too fancy with this. I set my early stopping to 15 epochs without change. I set my batch size to 50, and we're going to run it here, and you can see that it's working. All right, we're going to come back to this at the end, and I'm going to run you through the rest of it in a different window. Okay, so the first thing I did here was I did some data exploration. You can see that a lot of the variables kind of move in line with the seasons. Another thing you'll notice is we had a couple outliers. I replaced these with mean values from that particular variable. Then I want to take a look at correlation between variables. So here you can see that there was some high correlation. Maybe a better way to look at it was through the Seaborn package. This was pretty neat. So you can see, for example, temperature and rho are pretty highly negatively correlated, whereas RH and VPACT don't have the same correlation. You can also see the distributions of some of the variables. I did think about taking out some variables, so I took a look. I checked for multicollinearity. Uh, I probably could have taken out a couple of these variables. I kept them in with the hopes that the neural network would, take care of them. All right, so to start this off, I used a base model with just one LSTM layer with 50 nodes. Uh, I just ran it through for 50 epochs. Uh, Here's what it looks like. You can see we had some little bit of overfitting, so the test error increased after about 27 nodes. I ran the same model again, stopping at 27, and I ended up with an improved RMSE. Next thing I wanted to do was take a look at putting a dropout layer on the dense node. I tried a couple values. Zero point 0.2 seemed to work best for me, but this did not improve the RMSE. Uh, so I'll have to look at different ways to account for overfitting. All right, the next thing I did was I used one with 250 nodes on the LSTM layer, linear activation at the end. I run for 50 epochs and drop out of 0.25 on the dense layer. So basically, this is just a more complicated model with more nodes in the LSTM layer. This one worked better, and as up to this point, this was my best model so far. Next thing I wanted to do was make it even more complicated. I used three LSTM layers, used an additional dense layer with 50 nodes, set my patience equal to 5. Basically, the training would stop once the error didn't increase after 5 epochs. As you can see here, it was slight improvement. Next thing I wanted to do was I wanted to try adding dropout to the LSTM layers. So this dropout is either dropout before or after the LSTM node. The idea behind dropout, of course, is trying to help for overfitting, trying to make a more robust neural network. I also set the patience a little bit higher, so to patience equal to 10. So you can see here that this really didn't work. I was pretty surprised by this, but we're definitely running into overfitting problems. The test error increased drastically after 15 nodes, while the training error kept decreasing. This was pretty bad RMSE. So I think my conclusion here was that for this particular data set in this neural network, normal dropout to the LSTM really was not optimal. Next thing I did was decided not to do away with the LSTM layer or the dropout on the LSTM layers. I just stacked two LSTM layers, set a patience equal to 10, let it run, and worked pretty well. So this was another improvement. Um, kind of going along the same lines of keeping it simple seemed to work best. Next thing I wanted to try was recurrent dropout. So unlike the regular dropout, recurrent dropout is dropout within the LSTM layer. This I used two LSTM layers, one with a recurrent dropout of 0.25, uh, and this worked better than much better than the regular dropout, but it still was not an improvement as far as RMSE on any of our models so far. So basically, what I conclude from that is that the neither one of the dropout uh, functions worked especially well here. Next thing I wanted to try was bidirectional RNNs. I really thought this would work. Basically, what it does is it takes data from before and after the point in time to help the prediction. It seemed like with this time series and the temperature and various weather conditions, uh, not being random, it seems like there's quite a bit of the weather condition now definitely affects the weather condition an hour from now and vice versa. I thought this would work. So I ran this with an OSTM layer. I tried the bidirectional on the internal LSTM layer here. Uh, so this worked again. It worked okay. It didn't really make much of a difference, and my RMSE was slightly worse, which I was very surprised by. Another thing I wanted to try was smaller but no more numerous LSTM layers. So here I had three layers of 100 LSTM. I kept the bidirectional, and you can see that it was a little bit better than before, but still not our best model. The final thing I did was I used two GRU layers, one LSTM layer, 250 nodes each, and that was pretty much it for this one. This one ended up being my best model. I tried using NATM instead of Atom for the optimizer. The idea being that NATM has a little bit of decay for the learning. I thought this might help the model run longer without the patience early stopping kicking in. It didn't really work, so actually ended up not using the NATM and I used the Atom instead. Uh, so that's it. Pop back over to our other window, and we can see that the model works, and we had two epochs. All right, thank you very much.